Okay, so in this problem, we're going to be looking at a very simple type of pipe flow network where we have three pipes that are in parallel with one another. And what we're going to see is that there are really just a couple of little tricks that we have to keep in mind here, um, or a couple of little rules that we have to keep in mind here. And the first has to do with the head drop across the system, in this case from point A to point B. Um, And what we'll see is that because these three pipes are all starting at point A and ending at point B, then the only way for that to be true is if delta H1 is equal to delta H2 is equal to delta H3. And we can think of that as being true because this uh, change in head across pipe 1, 2, or 3 is really just due to a difference in pressure across that pipe, plus any difference in elevation across that pipe. And since they're all starting at the same point and they all have the same starting pressure and elevation, and since they all end at the same point, they all have the same ending pressure and elevation. And the only way for that to be true is if we have delta H1 equal to delta H2 equal to delta H3. So the other relationship that we have to keep in mind when we're considering flow through parallel pipes is that the total flow is equal to Q1 plus Q2 plus Q3, where in this case we have three pipes to consider, right? So we're just going out to the three pipes. If we had, in general, n pipes, we would have Q would be the sum of all of uh, all of the flow rates that start and end from those same points. In this case, we don't, right? We just have three, so Q total is Q1 plus Q2 plus Q3. And we can think of that more or less directly from mass conservation. Whatever material that we have coming into the system through point A is going to be split into three paths, right? 1, 2, and 3, and then leave again out through point B. And therefore, the sum total of flow rate that we have through pipes 1, 2, and 3 has to be equal to this total flow rate that's going either into the system at A or out at B, assuming that this fluid is incompressible. Okay, so let's look at the specific problem that we have here. So we're going to start with some assumptions. So right there, we're assuming it's incompressible. We're assuming it's Newtonian, and in general that the Moody chart is valid. Because that's what we're going to be using in this case to find our friction factors. And we're given a table here that summarizes all of our pipe data. We don't know what material it is, but we know what epsilon over d is for each of these pipes. We know the length, we know the diameter, we know the roughness. And also we are given in this problem that this is water with a density equal to 1,000 kilogram per meter cubed, and a kinematic viscosity nu equal to 1 times 10 minus 6 meter squared per second. And we'll actually see here, we haven't really talked about this in class, but kinematic viscosity is actually really convenient when we want to know Reynolds number, which we do in this case. It's also in SI units, a nice round number. All right, so we're trying to find the total flow rate Q through this system. And we're given that the total pressure drop is 150 kPa and the elevation drop is 5 meters. So our first task here is going to be to find the head, right? So first find delta H, right? I guess in the setup to this problem, this example 6.18 is supposed to come after a series pipe solution where they actually had already computed this, but we'll just run through that. So to find delta H, delta H is going to be PA minus PB, right, the pressure drop, divided by rho G. It's going to put it into something with dimensions of length or head, plus ZA minus ZB. If we work that out, so this is 150,000 pascals divided by 1,000, that's the density of water, times 9.1 plus 5 meters, and this works out to 20.3 meters. Okay, so that's where that total head loss comes from. So now what you can see is that for each one of these pipes, let's see, so what we want is the total flow rate, which is the sum of the three flow rates from the three individual pipes. And for each one of those individual pipes, we know that the head, or the change in head across that pipe, is 20.3 meters. Right, it's the same for all three pipes. And so basically we just have three pipe problems that we have to solve. And once we get the velocity, or in this case flow rate, for each one of those pipes, then we're just going to add them together to get the final answer that we're looking for. So start with pipe 1. So let's see, so we know H, we know L, we know D, but we want to find Q. Right, so this was one of our type 2 problems. Right, so remember in a type 2 problem, we're trying to find the flow rate or velocity. The thing that makes a type 2 problem a little bit tricky is that in general we're going to have to do some iteration, right? Because the flow rate depends on the friction factor, and the friction factor depends on the flow rate. And so because of that coupling between those two things, is not something that we can super easily solve for. We're typically going to iterate on this type of problem. And we have, looking ahead, we're going to have three of these types of problems to solve in this case. So to start with, to make our iteration just a little bit simpler, we're going to try to set things up for ourselves. So from the definition of the Darcy friction factor, we know that the head loss due to friction, let's say for pipe 1, it's going to be B squared over 2G times FL over D. And so to make things a little bit easier on ourselves, we're going to plug in all the values that we know here, right? And so we have 20.3 meters is equal to B squared over 2 times 9.1. I'm going to start omitting units here. We're going to assume that we're working in SI units, times F, right? That's also an unknown, times the length, which for pipe 1 is 100 meters, over D. And that length there is 8 centimeters. And so we're going to have 0.08 meters. And so if we work all of that out, let's see, so we're going to have V squared, we'll write this out. Hold on a second while I calculate this. So that's 20.3 times 2 times 9.81 times 0.08 divided by 100. So we have V squared times F is equal to 0.318. So V squared F is 0.8, or V is equal to 0.318 over F square root. So that way, if we know F, we can find V relatively quickly. So now we have to start with, guess for F1. Let's put our subscripts on there so we don't forget, because we have a few of these things to solve. All right, so we're going to start with a guess for F1. A good place to start for F1 would be the fully rough solution. So we're going to come up here. We note that we have epsilon over d of 0.003. And so coming over to our Moody chart for a roughness ratio of 0.003, so that puts us right about here, right? And that is going to correspond to a value right around 0.026. So we're going to be right around this line here. Scroll in or zoom in just again. This is 0.025, 0.026, 7, 8, 9, and that's 0.03. Sometimes it gets a little bit tricky on this log scale, but it helps if you make those markings yourself. And so we're starting in between the roughness of 0.002 and 0.00 here and 0.004 up here. So we're going to be right about at this value, which corresponds to a friction factor of 0.026. So let's start there in our problem down below. So that's from the fully rough solution. And so now compute V1 is equal to square root of 0.318 over 0.026 and 0.318 divided by 0.026 and then we're going to take the square root of that and there we go. Sorry, square root of 0.318 divided by 0.026. We're going to get 3.5 meters per second. If we now wanted to iterate on the solution, so on the test, this would be as far as I would really need you to go, right? Because actually, no. So on an exam, I would need you to tell me then. So then recompute or find F based on the new Reynolds number and iterate to convergence. And so in this case, actually, before we even know if we need to iterate, we need to actually check. Actually, first, check if RE is in fully rough. Because in this case, if we were in the fully rough region, we wouldn't even need to iterate, right? This would just be our final answer. So let's check our Reynolds number. So the RE, in this case, is going to be our velocity, 3.5 meters per second, times the diameter, which is 8 centimeters. So that's 0.08 meters over 1 times 10 to the minus 6 meters squared per second. That's our kinematic viscosity. You can see the units are going to work out here, so this will be dimensionless, which is good. So 3.5 times 0.08 divided by 1 times 10 to the minus 6th. And give me 1 second here. That's going to give us a Reynolds number, first Reynolds number of about 273,000. And with that Reynolds number, we can then go back up to the e minus 6. So we're going to get 280,000 these values that we have here, which is fine. So for 280,000, we're now going to go right back up here, check our Reynolds number. So 280,000, so that's 2.8 times 10 to the 5th. So remember, this was 1 times 10 to the 5th, 1.52, 2.53, 3.54, 4.5, and so on. So we're going to be just over 2.5, so right in this area. If we trace that up to where we were looking, yep, sure enough, we are in this zone where we have a transition from fully smooth down here to fully rough up here. And so we do in fact need to iterate again. So on an exam, after checking that Reynolds number, then you could say we are in the transition zone between fully smooth and fully rough. Therefore, iterate to convergence. Right? And that iteration would involve using this Reynolds number and the known friction factor to recompute, to find F. Once we've recomputed F, we'll recompute V, and then recompute Reynolds number. Let's just show one of those iterations here. So again, scrolling up, so we found at our Reynolds number of 280,000, we're going to be somewhere, just up, probably above where we were before, 0.0265 maybe, if that, for friction factor. And we're virtually converged actually already as fast as close as we can. I think in your text, it says that they're using the Moody chart, but then they give answers to 3 significant digits, which isn't really possible with just the Moody chart alone. So we have V1. Let's just say V1 is 3.5 meters per second. And now we're going to find Q1, right, given V1 is approximately 3.5 meters per second. And so Q1 is going to be pi over 4 times 3.5 meters per second times the diameter, which is 0.08 squared. This whole thing is going to have units of meters cubed per second. And so now if we plug that in, we're going to get Q1 is 3.14 divided by 4 times 3.5 times 0.08, and we're going to get 0.018 meters cubed per second. Your textbook puts this into units of meters cubed per hour, so let's just check. So that whole thing times 60 to convert to minutes, times 60 to convert to hours. Yeah, and sure enough, we get an answer of 63 meters cubed per hour, roughly in agreement with what your textbook gets, 62.5. And then the next step, I would do the same thing for Q2 and Q3. So just briefly, for this pipe number 2, we're given, in this case, that the epsilon over d is 0.002. So that means now we're right on this line here. Again, we're going to start in our guess in this fully rough region. Right, so anywhere along this line, we have a value of, taking this over, we'll call it 0.0235, right, because it's just between, this is 0.023 and that's 0.024. So we'll say for Q2, we're going to say f is approximately equal to 0.0235. We need to set up our method of solving for V2 though, right? So again, from the definition of the friction factor, we have that the total head, in this case 20.3 meters, right, is going to be equal to v squared over 2g, so 2 times 9.1 times f, L over D, and the length in this case is 150 meters and D is 6 centimeters. 150 meters over 0.06. If we work that out, so now we're going to have v squared f v2 squared f2 squared can be equal to 20.3 times 2 times 9.81 times 0.06 divided by 150, and that's going to be equal to 0.159. So, or V2 is equal to square root of 0.159 over F2. So with guess of F2, this was our initial. So with that guess of F2 is equal to 0.0235, we're going to get that V2 is approximately equal to the square root of all that. So let's see, so that's that's the square root of 0.159 divided by 0.0235. So V2 is roughly equal to 2.6 meters per second. So check RE is equal to 2.6 times 0.06 over 1 times 10 to the minus 6. So 2.6 times 0.06 divided by 1 times 10 to the minus 6, 156,000. We go up for our pipe 2, roughness ratio 0.02, a Reynolds number of 156,000. So it's going to be somewhere right around here. That is also in this transitional zone. So you can notice that we have actually a pretty substantial difference here. So we're going to start. So we're going to say that's our. So in this case, we do need to iterate. Right? So this is not fully rough. Therefore, we do need to iterate. And on an exam, I would allow you to just use this number. And so we would need to iterate to find final solution. In this case, we would iterate. So for example, we would say F2 is about 0.025 based on that Moody chart. So V2 and our next loop here is going to be square root of 0.159 divided by 0.025. And now we're going to get 2.52 meters per second. Therefore, Reynolds number is going to end up as 2.52 times 0.06 divided by 1 e to the minus 6, 151, 200. And now at that point, this is pretty much converged. So now to find Q2, this is going to be pi over 4 times 0.06 squared times 2.52, 3.14 divided by 4 times 0.06 squared times 2.52. So that's 0.0071 meters cubed per second, which is 25 meter or 26 meters cubed per hour. And we can do the same for pipe 3. We'll end up with Q3 is equal to 11 meters cubed per hour, and therefore our total Q is equal to Q1 plus Q2 plus Q3. It's going to be equal to 63 plus 26 plus 11. Right? That's 63 plus 26 plus 11, all in meters cubed per hour. So we end up with Q total is equal to 100 meters cubed per hour. So that's how we solve a problem asking us for a flow of pipes in series. We kind of skipped over the third pipe there. One thing to note, though, is that if had these pipes all been identical, we would have basically been done after doing the first one, right? Because the total flow would have just been the number of pipes times that total flow rate. The other thing to note is that as far as pipe networks are concerned, this is pretty much one of the simplest. So we're seeing here kind of the limits of doing things by hand. And in practice, for more complicated pipe networks, computational tools would definitely be used in a practical kind of situation. Still, this was a good chance to review the essential rules that we need to keep in mind when we're solving pipe networks or pipes in parallel, namely that the head drop across such pipes is all going to be equal, and the total flow rate through those pipes in parallel is going to be equal to the sum of all of the individual flows.